Dear students, welcome to my class on sharpness of resonance. What do you mean by resonance? Resonance is a phenomenon by which a forced harmonic oscillator oscillates with maximum amplitude at a particular value of the driving frequency. That is, when the driving frequency becomes a particular value, that is, the driving frequency approaches the natural frequency of the oscillator will oscillate with maximum amplitude. That phenomenon is known as resonance or amplitude resonance. We know that a forced harmonic oscillator is one which oscillates under the effect of an externally applied periodic force. If we apply a periodic force on a damped harmonic oscillator, it will continue to oscillate with the frequency of the external periodic force. That frequency is known as the driving frequency, and our oscillator will be having a natural frequency of its own. When this driving frequency approaches this natural frequency of the oscillator will oscillate with maximum amplitude, and that phenomenon is known as resonance. And the frequency at which, the driving frequency at which a post-harmonic oscillator executes amplitude resonance is known as the resonant frequency or resonance frequency. That is when the amplitude becomes maximum. Now we have another term related to amplitude resonance, that is known as the sharpness of resonance. We'll see what is meant by sharpness of resonance. Sharpness of resonance can be defined as the rate of fall in amplitude with the change in frequency on either side of the resonant frequency. See, if we can show the driving frequency on the x-axis, and if we put the amplitude on the y-axis, we'll get a curve like this. For the curve, this part shows maximum amplitude. At this point, when the amplitude is maximum, the driving frequency will be equal to the natural frequency of the oscillator. That is represented as omega 0, the natural frequency of the oscillator. Here, when the driving frequency departs from this natural frequency, that is, when the driving frequency becomes greater than or lesser than the natural frequency, we can see that there is a fall in amplitude. This rate of fall in amplitude when the driving frequency departs on either side of the resonant frequency is known as sharpness of resonance. If for small departure of driving frequency from the resonant frequency, if there is large change in amplitude or if there is large change in energy of vibration, then the resonance is said to be sharp. We'll see. Sharpness of resonance. The resonance is said to be sharp when there is a sharp falling or when there is a deep fall in amplitude when the driving frequency departs from the natural frequency of the oscillator. The sharpness of resonance actually depends on damping. That is, if damping is very low, the resonance will be very sharp. The fall in amplitude will be very high when the driving frequency departs from either side of the resonant frequency, either side of the natural frequency. And when damping is very high, when we are having an oscillator with very high damping, resonance will be flat. The curve will be very flat. That is shown in this figure. In the case of an oscillator with very high damping, the curve will be like this, which we can call it as a flat resonance. And in the case when oscillator is having low damping is very low, the curve will be sharp. This curve will be sharp, and we can say that the resonance is sharp. An example for sharp resonance is sonometer. We have done the sonometer experiment in your plus 2 classes. There you can see that on the sonometer wire, when a paper rider is kept, and if we place an excited tuning fork near to that, at a particular frequency of the excited tuning fork, the paper rider will fly off from this sonometer wire. That is an example of sharp resonance, and that occurs at a particular value of the driving frequency. And there are examples for flat resonance also. A common example is resonance column experiment. That also you all will be familiar. for an air column, if an excited tuning fork is placed and the length of the air column is changed, we can observe that near the resonant natural frequency, when the frequency of the tuning fork approaches the natural frequency of the air column, amplitude resonance start to occur, and it will last for a few seconds, and then amplitude will gradually come down. That is, there is not a sharp, there we cannot observe a sharp increase in amplitude, but there will be a gradual increase of amplitude and then gradual decrease. That is an example of flat resonance. So resonance column experiment is an example for flat resonance, and sonometer is an example for sharp resonance. Sharp resonance occurs whenever the damping force is very low. For high damping, resonance will be flat. That is, the curve will be flat. Now we will see an LCR oscillator as an electrical analog to a mechanical oscillator or a damped harmonic oscillator. That is, an LCR oscillator means an inductance, capacitance, resistance circuit when it is connected to an external AC voltage. When a potential difference is applied across this inductance, capacitance and resistance circuit, it becomes a forced harmonic oscillator, or it is analog to a mechanical oscillator. We will see how. That is, if an LCR circuit is an external voltage is applied to, or potential difference is applied to an external, is applied to an LCR oscillator, we can see that, you can see here, the potential difference across the inductor will be equal to VL, which is equal to L into di by dt, where L is the inductance and di by dt represents the rate of change of current. But we know that rate of change of current is equal to rate of change of charge. That is, I will be equal to dq by dt. So di by dt can be equal to d square q by dt square, where q is the charge. Then the potential difference across the inductor is equal to L into d square q by dt square. Now we have, we have the other component, resistor. For the resistor, we can see that the potential across the potential difference across the resistor is VR, that will be equal to R into I, resistance into current. That is equal to R into again dq by dt. Now we have the third component, that is capacitor, and potential difference across any capacitor will be equal to Q by C, where Q is the charge and C is the capacitance. So the sum of the potential difference across each circuit element will be equal to the external applied voltage. The sum of the potential difference of these three components will be equal to the potential difference of the externally applied voltage. That is, L into d square q by dt square plus R into dq by dt plus q by C will be equal to V applied, which is the externally applied voltage. Now you can see that this equation is similar to the equation of a forced harmonic oscillator, that is m into d square x by dt square plus b dx by dt plus cx is equal to F applied, the applied force, where m is the mass of the oscillator, b or gamma is a damping coefficient, and k or c represents the force constant, which is equal to applied force. In LCR oscillator, the electric charge, actually what happens is, in LCR oscillator, the electric charge oscillates between the capacitor and inductor through the resistance, similar to the mechanical oscillations of an oscillator. The resistance, actually the resistance is this element which causes dissipation of electric charge, which is similar to the damping which causes dissipation in a mechanical oscillator. So damping causes power dissipation or energy dissipation in a mechanical oscillator. Similarly, the resistance causes a dissipation of electric charge in this LCR oscillator. So these two equations are similar, and we can say that an LCR circuit is an electrical analog to a mechanical oscillator. We will see how can we compare these two, mechanical oscillator and electrical oscillator. That is, mechanical oscillator, in the case of a mechanical oscillator, the mass will be similar to or analog to inductance of an electrical oscillator. The component of inductance L is analogous to the mass of a mechanical oscillator. Mass of the oscillator will be analogous to the inductance. Then in the case of an electrical oscillator, there is charge which is similar to or analog to displacement x. Also, electric current I equal to dq by dt is analogous to the velocity. That is, velocity of the oscillator V equal to dx by dt. Then we have the electrical resistance similar to the damping constant gamma or damping coefficient B or damping coefficient which can be represented as gamma also. Then reciprocal of capacitance 1 by C will be similar to the force constant C or K. You can take it as C or K. That will be equal, analogous to the reciprocal of capacitance. So this is a small comparison of the above two equations of LCR oscillator and a mechanical oscillator. These are the components of an electrical oscillator which are analogous to the components of a mechanical oscillator. Now, from this you can infer what will be the frequency of an LCR oscillator. This is a small assignment for you. Find out the frequency of an LCR oscillator from these two by comparing the two equations for mechanical oscillator and LC oscillator. Thank you.